Good morning. So we had started chapter 2. We said that we're really, diving into the physics now. So all of the problems, all the examples that we're looking at, everything now is very relevant to getting yourself through the course and the kinds of things that you want to prepare for. What the midterm exams are going to be based on are kind of the problem-solving techniques that you'll see here in class, in the examples that we have here, and then also in the homework problems. So again, the advice is to make sure you're staying caught up in the course and make sure that you're stopping by office hours with whatever kind of questions that you that have come up. All right, so we had, in chapter 2, we were looking at this topic that we called kinematics, and we said that fundamental to kinematics is being really, really clear about definitions of displacement, definitions of velocity, and definitions of acceleration. And we were kind of in the middle. We had introduced acceleration and how to go about calculating average acceleration. And now we're ready to come back and take a look at what we're going to call instantaneous acceleration. So just a quick review of kind of where we came from here. We had looked at acceleration of objects, throwing objects up in the air, for example. In this example, example 2.5, 2-5, showing velocity as a function of time and what was going on with the accelerations here. We had cars that were slowing down. So now we're ready to go in and develop some of the mathematics, some of the formulas that we want to be able to work from for instantaneous acceleration. So we want to know, instant by instant, how much is the velocity increasing or decreasing, and that will tell us the acceleration. So we're going to use the very same formula that we used before for velocity, only this time we're going to take shorter and shorter intervals of time, same thing we did before, but this time we're going to be looking at variations in velocity. We're going to be looking at delta v divided by delta t, and in the limit we're going to call those infinitesimals. So those are going to become dv divided by dt. So a couple different ways. We can say the acceleration is based on taking the derivative of v with respect to t, but another way about thinking of this is it's just a ratio of numbers. So dv represents a tiny variation in the velocity that occurs during a tiny interval of time. So the graph that we're looking at now, so we're looking at graphs, and we did this in the last lecture. So again, when you look at a graph, look at the axes. You've got to know what the axes are telling you, otherwise you really don't know what the graph is trying to present. So in this graph, we are now looking at v as a function of t. And previously we looked at a bunch of x versus t graphs, and we took limits of delta x over delta t to get velocity, but this time it's delta v divided by delta t, and we're getting acceleration. So this time, the vertical axis is velocity. Here is a function, so we've collected a bunch of data on the motion of some kind of an object, and we can say just how fast it's traveling as time progresses. And what I'm seeing from this graph is that this object starts out going not as fast, but it rapidly increases its speed, and then that rate of increase drops off a bit, and then here it's starting to pick up again. Okay, so this graph reminds me of our best measurements of the expansion of space. Anyway, so if we trace back the history of the universe, we find out that the evidence suggests there was an early period where things were rate of separation. Now these are velocities, but for expansion of space it would be the rate at which space is getting bigger. And space was getting bigger at a pretty high rate for a few billion years. And then for a few billion year period, for several billion years, that was decreasing. It was still expanding, but the expansion rate had slowed. But observations made over the past 20 years or so, indicate now that the rate of expansion is increasing. And so that's what's happening in this graph here. So here, it's just some kind of an object, and it's really picking up speed at a pretty good clip, and then it's picking up speed that not at the same rate, and then it's picking up speed at a faster rate again. So the acceleration, we said, instantaneous is given by dv dt, and we know that a ratio of dv dt is given by the slope of the tangent line to that function. So we can actually go from different locations along this function, draw a tangent line in, and whatever the slope of that tangent line is, that is going to be the instantaneous acceleration at that particular instant. So there we go. That's how we're going to define acceleration is defined as the ratio of dv dt. The graph before was x versus t. So the average acceleration, the one that we've been looking at, is the slope of the line connecting point 1 and point 2. Now those are just endpoints. So the endpoints are saying there was an instant in time where we were going this fast, right? We were going at speed v1, and then there's a later instant in time where we're going at speed v2, and if we just want to average that effect, we can take the delta v, which is v2 minus v1, and divide that by the delta t. This is rise over run, and that'll give us the slope. And that line connecting the points will have the slope of delta v divided by delta t. But that's based over a rather large time interval, and in order to get the instantaneous slope, we have to shorten the times. So the tangent line here would give us the acceleration at t1, and a tangent line here would give us a slope at time 2. And the acceleration at point 1 is larger than the acceleration is at point 2. And compared with the average values, the acceleration was higher at point 1 than average, but at point 2 it's lower than the average value. So you can kind of see how that averaging worked out for that. All right, here is an example. Example 2.7. If we are given a function, now we talked about this before too, that often in our math classes or our physics classes or engineering classes, we're given a formula and then we're just asked to carry out some mathematics on that formula. But in real life, if we're following an object and we want to find out what its velocity and acceleration is, we have to collect data. So we actually have to devise measuring instruments that are able to go in and collect all the data, and then we can take the data, plot that on a graph, and then we can search for functions that would represent the data. Okay, so it's observation driven, it's data driven. Now here is an object that they're referring to. That word is pronounced object. It's moving in a straight line, and we've collected a bunch of data and we've found out that its position as a function of time is given by a constant 2.10 meters per second squared. Now that sounds kind of like an acceleration value. Is that the acceleration of this object? It's got acceleration units. And then there's a t squared here, and so that's telling us that we're going to get units of seconds squared. That will, the units check out. So the units look correct. And then at t equals 0, well, at t equals 0, this object is at 0. Oh, no, I'm sorry. You got to read the next line. Okay. it's starting out at 2.80 meters. It's the same numbers we had before, right? It was that same problem, was it? I think it was. So this is the same function that we had before. We're not starting off at 0 meters. We're starting off at 2.8, and that's why it looks like this. So we can draw 3 graphs. You should be able to draw 3 graphs. So you should say, yes, I can look at this. I can, from the function given, I can determine what the velocity function will be. I can determine what the acceleration function will be, and I can draw graphs for all 3. I can draw x as a function of time, v as a function of time. What intervals are we looking at here? So they want, oh, again, it's going between 3 seconds and 5 seconds. So it's kind of a follow-up example to the one that we looked at before. And but what we want to do is draw these really nice graphs here. Yes, you could be asked to draw these on a midterm exam, so be prepared. So here's the function here. Now it looks like a parabola, right? It's x, it's got a constant with t squared with another constant. So this looks kind of parabolic. This is looking kind of like a straight line. In fact, the function they came up with, 4.20 times t. And then this looks like a straight line also, but a straight line with no slope. So let's see how that all happened. So I wrote this as assume, and maybe they've collected a lot of data. So anyway, the displacement as a function of time is given by that formula with these constants. And so what we can do is, we'll get to this part later. I'm going to start over here. V is dx dt. So in order to calculate dx dt, we know what those rules are because we took calculus. And so what we're going to do is we're going to look at this. We're going to bring down the factor of 2. T is the variable here. A is a constant. So we're going to bring down the factor of 2. We're going to get a 2 out front with an A and 1 power of t left. Now b is a constant, so when we take the derivative, that just goes away. So the velocity, if this is x as a function of t, then taking a derivative with respect to time will give us v as a function of t. Taking another derivative, again with respect to time, will leave us with this function. The t will drop from 1 power down to none. We'll keep the constant. It's going to be 2a. So following those, the rules that you learned in your calculus courses during first semester calculus provides a way to go from x as a function of t to v as a function of t to acceleration. And I know in calculus classes this is one of the favorite examples they like to work from. This is such a nice, clean, clear example of how we can take derivatives and get information about velocities and accelerations. Now, what we're finding here then, let's take a look at the acceleration. The acceleration is constant. Now, why did the acceleration turn out to be constant? Turns out the acceleration is constant because the highest power of t in our formula for displacement that we started from, the highest power of t that we had there was second power. So we had t squared. We did not have a t to the third power. Think about that a minute. If we had had a t to the third power, then taking a derivative would have dropped that to 2. Taking a second derivative would have taken it to 1, but we would still have time dependence. So the fact that the position was given by, first of all, the formula we're given was a polynomial. Okay, it wasn't a sine, it wasn't a cosine, it wasn't an exponential, it wasn't a logarithm, and those could all be formulas we use for motion. So the motion we're looking at is being described by a polynomial, and the polynomial is order 2. It doesn't go higher than that. Anything that has a polynomial form with order 2 in it for time is going to give us a constant acceleration. Now what we've determined here is that the acceleration, remember we've kind of wondered if a was the acceleration because a starts with, a is the first letter in acceleration. It had the right units for acceleration. It turns out that that's not quite right. the acceleration actually is given by 2 times a. So if a is 2.10, the acceleration actually is 4.20. So we have been able to determine what's the acceleration, and in this example, it's a constant acceleration is what we've found. So we've got a constant acceleration of 4.20 meters per second squared. Now, what else? I wrote what we often refer to as x naught. Now we've been using x1 and x2 a lot, but I want to shift over and start using, and the textbook does this too, we want to start using x naught to represent where was the object, where was it located, what was its position when t was equal to 0. So when t is equal to 0, x naught, the starting location, is equal to b, so b turns out to be x naught. Now, I rewrote the formula this way. So let's, instead of writing it as big A, t squared plus big B, what if we wrote this as x is equal to 1/2 times little a, where little a is the acceleration, times t squared plus x naught. So instead of putting these constants in, we're going to designate them. We now know that whatever we put in for b is x naught. It's where we started out, and whatever we put in for a is half of the acceleration. So the acceleration is actually twice as much as whatever constant big A is. So now that we've learned all that, anytime we have constant acceleration, we can start using formulas that look like this. And we'll derive some that are even a little more general than this formula. But that's the formula we could think of as using. So once we've got these numbers developed, we could use these two values for a and for x naught and work from this formula instead. So they wanted us to find out at t1 equals 3 seconds, and at a later time, 5 seconds, where are we located, and what's the velocity and what's the acceleration, and now we've got the formulas. So the difficult part was getting the formulas set up correctly, and now we can plug numbers in and then check. Okay, you always do a reality check on every problem. So let's take a look and see. I ran this, I got 21.7 meters, 55.3 meters for at a later time. Those numbers seem reasonable based on what we had done in that earlier example. I do want to go back and look at the graphs. So I definitely want to go back and look at the graphs, stare at the numbers we get, stare back at the graphs, and ask if everything is consistent. So much of science and engineering is based on double and triple and quadruple checking every single step. Every step of the way you want to check it. You always want to ask yourself, is that the right set of units? Is that a reasonable number that we've come up with? So, sometimes students will hit the calculator, they'll make an error on the calculator, they get an answer, instead of 21.7 meters, they write down 217 million meters, and then you go back and you look and you go, well, didn't you see that it was 1,000,000 meters? And you go, oh, that's what my calculator said. So, which is not a good answer. So much, again, of science engineering is checking and double checking results. Asking yourself at every step, is that really a reasonable sort of number to be getting? So anyway, we ended up with these values for displacements at these particular times. And then I took the 3 seconds and plugged into my velocity formula right here, and got the 12.6. And then I plugged into now the acceleration is constant. So notice the acceleration is coming out at 4.2 meters per second, all the way through the entire acceleration. Yes, we are picking up speed, so this needs to be bigger than everything seems fine. Let me graph it. So I'm going to go back, now that I've seen all my numbers, and notice they've written in the formulas as a reminder, so we can see where these formulas now are coming from. And yeah, that's what constant acceleration would look like. It's at a constant fixed value of 4.2. And so that's what's on the graph. That is the value of 4.2, and it started out right at t equals 0. Right when we begin to pick up speed, that's an acceleration, even though at time t equals 0, we started at 0 velocity. The acceleration was not 0. The acceleration became 4.2 meters per second squared, and we're going to say that happened sort of instantaneously. So at one instant, the object was sitting there at rest, and then it took off. And from the moment it began to pick up speed, it had this acceleration, which means at t equals 0, its velocity was 0. Okay, so the graphs check out. I mean, I'm looking at these numbers of 10, 20, 30, 40 meters, 5, 10, 15 meters per second, and then the acceleration's constant. The time axes are listed from 1 to 6 seconds. That provides, you know, a very nicely scaled graphs, and that's something you guys should aspire to. You want to draw nice graphs that are very informational, show very clearly what's happening, pick familiar numbers, and for the time axis, one, you know, just integers works well. Here, since we've got to go between 0 and 60, let's divide those up into tens. Between 0 and 25, let's divide those up into fives. So pick numbers that are sensible and make use of the full graph. So see how we designated a certain amount of area for the graph, and then we labeled the axis in a way where the graph would fill the entire region. So the data is not just pushed over to one side. So graphs are very useful, very informational. Practice those. Okay, good example, right, with constant acceleration. Oh, there's more? Okay, so this is going back, and was this in the original problem, or did this get out of order somehow? Oh, the average acceleration. Oh, yeah. So I actually did part B first, which is, I guess I just, yes, okay, I've got it. So I just filled in all of that stuff, yeah. And so the average accelerations, we can go back, and it turns out that the average acceleration for this case, because the acceleration is constant, the average acceleration is going to be the same value. So that's not a big surprise. So we did the formulas using both approaches. Yeah, I kind of confused myself there for a minute. So we took this new approach of getting instantaneous velocities and instantaneous accelerations. So those are instantaneous. And then we came back and compared with average accelerations, and it turns out for constant acceleration, they're the same thing. And we'll look at a lot of examples where we have constant acceleration. Okay, so for this example here, conceptual example 2.8, we're using some graphs. We're analyzing the motion here. And it says that we have two cars, car A and car B, and we are plotting their velocities as a function of time. And so that's kind of interesting. Car A and car B, during a 10-second interval, let's see what we can say from the graph. During a 10-second interval, have accelerated, oh, the words are telling us the same thing, from 0 to 100 kilometers per hour in 10 seconds. So compare average accelerations and instantaneous accelerations and total displacement for the two cars. Now, I'm thinking the average acceleration is going to be the same, because average accelerations only depend on what? And the average accelerations only depend on delta v and delta t. They only depend on endpoints. And during the same time interval, the same delta t, both cars experienced the same delta v. Now, car A had a higher acceleration initially, but then the acceleration dropped off, and as a result, it ended up reaching the same speed during the 10-second interval car B. Car B did not start off with as high of an acceleration, but at some point its acceleration, see how the slope here is now greater than the slope here? So its acceleration was sustained, and so it also was able to reach, so I'm going to say on part A the average acceleration is going to be the same for both cars. What about instantaneous accelerations? And the instantaneous accelerations are different, right? Compare. And so the instantaneous accelerations are just what we talked about. The slopes, it's a v versus t graph. So the instantaneous acceleration will come from looking at the slope at different locations. So initially the acceleration of car A was higher, but even by the time we hit 2 seconds, see how the slopes there are becoming much more similar. I would say by 4 seconds the acceleration of car B is matching or maybe even a little higher. Probably similar. By the time we hit 6 seconds, certainly car B's acceleration is higher. The slope is steeper than the slope on car A's path. Now, what about the total distance traveled by the two cars? Did they travel the same distance? Because it looks like during the same time interval, they both reached the same maximum speed. Did they travel the same distance? Now, distance is going to depend, displacement is going to depend on how fast, we have to add together how fast they were traveling at all the different times. Now, what did happen is that even though they both reached the same speed, at all times car A was traveling faster than car B. So if you consistently travel at a higher speed during the same time interval, I'm guessing that's going to lead to a larger displacement. You're going to travel farther if that's the case. So let's take a look and see how our reasoning worked. So this is a v versus t graph, and v is in meters per second, t is in terms of seconds alone. A has a higher acceleration at first and not as much acceleration later on. So yeah, the average acceleration should be delta v over delta t. They both had the same delta v. They both had during the same delta t. And that says the average acceleration for both cars, they're going to be the same thing. Now, for part B, the instantaneous acceleration, same thing we talked about. The slope at each instant, if I look at, now so what I tried to do was this. I tried to take an acceleration as a function of time. So if I do an acceleration as a function of time, what that required me to do was to go back and take a look at this graph. So what I did was I said the acceleration for A, first of all, it's really, really steep, and then it drops off. Now car B doesn't start off as steep, but it drops off more gradually. So kind of halfway through, the slopes match. And that would say that car A started off with the higher acceleration, and then the acceleration dropped off, is the way I wrote this. And then car B started off with not as high of an acceleration, but at some mid-bit, its acceleration didn't drop off as quickly. And so I tried, at 4 or 5 seconds in, they both had the same acceleration, and I estimated that from the slopes on those lines. Now, on an A versus T graph, the area under here is going to be the final velocity that you have acquired. So they both have to have the same area underneath. So if I've drawn these graphs reliably, they look okay. So the area under the A curve and the area under the B curve have to match, because that would be the final area, final velocity reached. Now for displacement, again, we could use graphs, but this time we want to use the v versus t graphs, and well, we've got those. So we could actually go back to these more carefully drawn graphs. This is v versus t. The areas under those curves are going to tell us what the total displacement was. And so, yeah, we have a nice graphical technique of saying car A has traveled that slice right inside here. If we determine the area of that, we could determine how much farther car A traveled than car B. We could estimate what the areas under those curves are to do that. Okay. So using graphs is really useful. And so yeah, I am gonna, I will definitely be asking you to use graphing in problem solving on things like midterms and such. Okay, so here's motion at constant acceleration, and the average velocity of an object during an interval time is delta v over delta t. That's the average velocity, and we can get that by taking x minus x naught over t. Now what's interesting here, and this when I first took physics, this confused me so much, I hope there's a fairly simple explanation for how this works. So we would start with velocity, and it would be delta x over delta t, and with the delta x, this became x minus x naught, which is fine. The delta t became t minus t naught, and then we just drop the t naught. Now the assumption here is that the t naught is always going to be what? And it's kind of like saying, well, the t naught could be 0, and that would mean delta t can just get replaced by t, and that's what we tend to do. So there's kind of this period where conceptually we want to think of t as a time interval, but just for convenience in our formulas, we drop the delta and just start calling it time. So, and kind of the assumption is that the time that we started at was 0. Okay, you could think of it that way. So don't panic. I did panic when apparently people were using delta t and t sort of interchangeably, and I thought, well, that can't be, but it can. Mathematics is a tool that we use, and so we have to attach meaning to the symbols that we use in our mathematical formulas, and that just means that, yeah, if I want to think of it conceptually as delta t and it matches up well with the delta here, if I want to simplify the formulas later on, I could stop using delta t and I'll just use t, but it has to be clear about the meaning, so it doesn't mean you can just be random with writing down formulas. It just means when you write them down, you have to write them down, use them in a way where each symbol has a certain meaning to it. So anyway, what we could do then is say that the acceleration that we have, the acceleration, if it's assumed to be constant, is given by v minus v naught over t. We're doing the same thing that we did with the average velocity here. If the acceleration is constant, then the average acceleration will be the same thing as the instantaneous acceleration. So for constant acceleration, we can use v minus v naught over t, but if we're accelerating, that's not a velocity formula, that's only an average velocity formula. Okay, so in addition, what we can do is say that if we're undergoing a constant acceleration, now a constant acceleration means that you're picking up speed at a steady rate, so, or you're slowing down at a steady rate, right? So either the velocity is increasing or decreasing at a steady rate. The average velocity then can be found by taking some starting value, adding together some final value for velocity, and dividing by 2. Because the velocity was increasing steadily, it was increasing linearly, the average value during an interval is found by taking the final and initial velocities and finding the average value. So when we combine all these formulas together, we end up with a very useful formula that gives us the position of an object as a function of time, and that formula is x our position at a certain time, is equal to, we can determine that value by knowing where the object started, adding on its initial velocity. So v with a little 0 off to the side, or a little o, is called v naught. The initial position was called x naught. V naught times t tells us the effect of having already been moving when we started. So, and then finally, if there's an acceleration going on and it's constant, we add a term 1/2 at squared. If you think about it, what would happen if we didn't have an acceleration? Well, if we didn't have an acceleration, this term would not be here. This is the acceleration effect on displacement. And v naught would just become v. And we would have x naught plus v times t. That would be a formula for constant velocity. But since instead of constant velocity, we're working with constant acceleration, we have this additional term that takes into account, provides for us the effect of undergoing a constant acceleration. That's a formula we're going to use a lot. Okay, now not all accelerations are constant, but a lot of different types of accelerations can be roughly approximated as constant. And some accelerations are very close. So it becomes a very good approximation for many situations. Now, a little more algebra tells us this. If we combine the equations, we can also eliminate time from the formulas, and we end up with an additional formula. So here is kind of the combination of everything we've done in the last few slides, and you can go back and check the algebra on this. But more important, and you should at some point check the algebra, but even more important is learning to make use of these formulas that we have now derived. So these are what are called the constant acceleration kinematic formulas, and we're just going to use these a lot. Almost all of the problems that we look at in this chapter and the next chapter and maybe the chapters, for the first 3 or 4 chapters, we are almost exclusively going to be looking at situations where we do have constant acceleration, or where constant acceleration is a very good approximation. And that means we're going to be coming back to these formulas almost every problem. We'll be coming back to some form of these constant acceleration formulas. In fact, you guys are going to get so attached to these, when we move on and look at different sorts of motion that's not constant acceleration, you're going to want to keep these, and you have to let go at that time. But for now, embrace these, and hey, these are the formulas we want to be able to work from. Now, you know, there's always this discussion of what's physics? Is it just plugging numbers into a formula? Just get the right formulas. And so physics is a combination of conceptual understanding of what's going on. And I hope what you can see from the presentations here, that everything that we've done, everything I've tried to do, is to build an intuition of what is going on here. What is happening? If I had to write a quick sentence describing what's going on, can I do that? So physics is certainly dependent. We certainly work from formulas, and we derive formulas to find out how to best understand what's going to happen in a given situation. But we want conceptual understanding behind all of this. So when you're working on a homework problem, when you're looking at examples from lecture, talk to yourself. Or, you know, if someone else is around, talk to your study partner, your study buddy. Discuss what is it that's going on here? Why does the formula look like this? Why are these formulas going to work? Because you really do want to build up that intuition of what type of a situation is it that I've been given, and what will work in solving the problem. So anyway, let me get back to these. So this is saying if something's undergoing a constant acceleration, A, then the speed, or the velocity, depends on how fast we're going to start out, plus the effect of the acceleration as time progresses. This is V as a function of t. this is our displacement formula, and we've talked about this one. This is x naught, where we started. V naught is now how fast we were going, the same V naught as here, times time. But now the acceleration term is 1/2 at squared. And a lot of times students go, well, where's the 1/2 coming from? And go back and look at those earlier slides. We could see when we were taking those derivatives why the 1/2 is there. Okay, so we don't get the full effect of at squared. We get 1/2 at squared. And then finally, this is x as a function of time. This is really handy too. So sometimes in a problem, they don't give us any information about time, and they don't ask for it. Instead, they focus on how fast our object's traveling over what distances. So what we can do is we can eliminate t between these two formulas, and that gives us formula 3, where the velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. So, and I put I highlighted this, so I put my highlighter on this, because I'm going to say those are the 3 really important formulas. Now there's a fourth one, and some textbooks like to use this, some not so much. There is a fourth equation that can also be used, and that's the average velocity. And occasionally I find use for that, but I almost always, 95% of the time, I'm able to get everything solved using those first 3 formulas. Okay, here's a set of, here's the advice in problem solving. Read the whole problem, make sure you understand it, then read it again. So that's such good advice for me, because I was saying earlier, I have to be disciplined with myself. I like sometimes to just skim a problem where I really need to read it carefully. And then what you can do is you can write down the information that's down here in step 4. So I'll go in order here. I think it is worth stepping through this. Read through the whole problem, make sure you understand it, and then once you are certain that you understand it, read it again. I think that's such good advice on these homework problems. Decide from your reading of the problem, which objects are we really looking at? Like in those earlier examples, we were looking at cars speeding along the highway. We weren't looking at the highway, right? We were looking at the cars and the motion of the cars in particular. Now that seems maybe pretty straightforward now, but as problems become more involved, it's going to become important to isolate one object at a time and be very clear which objects we're talking about. So which objects are being looked at, and what is the time interval? That seems like anyway, so, and look at the time intervals going on. Draw a diagram and choose a useful coordinate system. So once you've identified the objects that you're looking at, draw a diagram and choose coordinates. I think the time interval stuff fits in here. Notice how many of these drawings involve snapshots in time. So I want to look at what happened at t equals 0. I want to see what happens a few seconds later, maybe draw multiple diagrams showing the progression, the time progression of what's going on. So read the problem, understand it, then read it again. Isolate the objects, draw diagrams, choose a useful coordinate system to work from, label that with X or T or whatever you need to on your diagram. Write down the given quantities. So in a problem, everything that's listed, write down that information, write down that number, and assign it to whatever variable you want to work from. So work from a set of variables that make sense. Well, I'm going to ask you to use the variables that we're using. So let me go back and say that. Just so that we're kind of all on the same page here, it's more helpful if you use kind of a standard set. If you occasionally develop separate Anyway, we'll see how this works, but try and stick with standard variables for these quantities. And then you got to ask yourself conceptually, what goes on here? Talk yourself through the setup. So that's my added advice here as to what's going on. Now, it goes on. So part 6 says, which equations are going to be relevant? So let's pull out equations that we plan to use. We might not use them. So this is also something to be aware of, is that when you're solving a problem, you may have to change course. You may start out by assuming that these are the relevant equations in solving a problem, and then find out that that actually wasn't quite what you needed to work from based on the information that we were provided. So it's fine. So try different things out. You have to find the balance between trying things out and slowing down and stopping and thinking carefully. So it's possible to just try too many things out, spend a lot of time just kind of going in random directions without much guidance. But it's also possible to hesitate and go, I don't want to put pencil to paper until I know each step. It's a good chance you won't know all the steps until you've started working through the problems. On number 7, it says calculate the solutions and then round to the appropriate number of significant figures. And I'm going to say you can get away with one additional significant figure. And then look at the results. Is it reasonable? Does it agree with what you would think of as being a rough estimate? Sometimes in physics there are surprises. The answers are very surprising. And you go back and you double check something and you go, that's really it. It really works that way. And that becomes a real opportunity to go in and kind of build intuition to where you say, wow, I never would have expected that would happen, but I can now see why those are the numbers. But in most instances, if you get something that's just crazy, right? If you have a car going down the highway 1,000,000 meters a second, you're going to think, nah, something went wrong. I hit the calculator. I hit something wrong on my calculator. I better go back and double check it. So always check the results. Check it both numerically and check the units at each step. Okay. Well, I think that's it. Now, I don't know if these are the official 9 steps. Maybe there's 10. Nope, it was 9. So anyway, that's all good advice. Okay, so that's something worth thinking about as you look at these problems. All right, so let's do some more problem solving here. Example 2-10, acceleration of a car. So here's a car traveling along the highway. I think the object we want to isolate here is the car. So we're looking at the car. We're told that there is an acceleration. Yes. So we're told that the car starts from rest. They're at a red light. Light turns green. And the car begins to pick up speed and goes across the intersection. So this, I guess between the building and the tree, this is an intersection. Car was stopped at a red light. Light turns green, they pick up speed, and they travel 30 meters. So it's a pretty good sized intersection. So it's 30 meters. Wow, that's a big intersection. That's a really big intersection. So 30 meters across this intersection, and we're going to be accelerating at 2 meters per second. How much time is that going to take? Okay, so we've got the setup. Let's take a look at this. So the given information is I have to travel a distance of 30 meters. Now notice I kind of intentionally used d instead of x, just to show that's fine. We'll see how we'll adapt to that. So I'm going to say that there's a distance of 30 meters, and I'm not quite clear yet. Is that an x naught? Is that an x? Where is it going to fit into these? And so I just wrote that down. Now the acceleration is 2.00 meters per second, it's saying. So I'm going to write that down also. So here's my diagram. Here is the car at t equals 0. And here is the car at some later time. It has traveled a distance d. Ooh, I left off my velocity and acceleration arrows. I apologize for that. I should have done that. I almost always do. Yeah, they've got acceleration. And I think putting in a velocity arrow in there should be good too. Now, I wrote down all of those constant acceleration formulas. They said the acceleration's constant, so I wrote all the formulas down for that. And then I kind of stared at them, and I said, what is it they want us to find? And they want us to find the time. So this is given. I wrote the diagram. They want us to find out what t is. So I'm thinking, I'm probably not going to use my third equation, right? Because, hey, there's no time here. These are the two that have time as a variable. So now I wrote, well, I'm working from both these equations so far. Let's think about putting some numbers in for x naught and v naught. Now, x naught is 0. We can define x naught to be 0. I think that's a sensible, almost always, whenever you can define x naught as 0, why not? So I went ahead and defined x naught as 0, and it said we started from rest, so v naught is 0. There's no question there. So that tells me that this term drops out. Well, that formula got easier. And these terms drop out. Well, that formula got easier too. Notice that with x naught equals 0, v naught equals 0, I now can say that x, the final location, will be 30 meters. I had to make sure that x compared with x naught indicated a distance of 30 meters, and I have done that. So I've got these variables now set up, and I don't really know what v is, but looking at the second equation here, I don't know what v is at the other side of the intersection, but I do know what x is. So I know x, I know these guys are 0. I can solve for time because I know the acceleration. So notice how that formula is simplified, and I think that's a good step. I think you always want to start with the general formulas, certainly at this stage, starting out in chapter 2, start with the general formulas, start with the given information, and start assigning values to the x naughts and the v naughts and the whatever information is given. And then once you've done that, write the formula that you intend to use, simplified. And that's what I've done. I go, oh, look how it simplifies. That is, this was a little terrifying. When I saw this, I thought, that's a lot of stuff going on. Oh, that's easy enough. If I start from rest, at x naught equals 0, it's going to be so much easier. So I started from this equation and solved for t. So that's what I was after. And when I plugged the numbers in, and I plugged them in right here, 2 times my 30 meters divided by 2 meters per second took a square root, and it says the time here is to 3 significant figures, 5.48. This one, I don't know, you could, 5.5, 5.48. I'm going to keep 3. So that's going to take 5 seconds to get across the intersection. Okay, this person had better hurry. They better cross the intersection faster than this. It is a big intersection, but they don't want to take 5 seconds getting across. Of course, you don't want to race across either. You want to drive responsibly. But do the numbers make sense? Well, yeah, it was a pretty big intersection. I can imagine 30 meters would be a third of a soccer field in distance. That's a pretty good distance. The acceleration was not too big, and so the acceleration being pretty small here resulted in taking 5.5 seconds to get across. Now that's the approach. That's all the steps. So I feel pretty good about it. I'm going to box my answer and turn it in. Okay. I'm going to lock in my answer. Now, I added a couple things here, so I was kind of curious, how fast would the car be moving? I was a little worried with that acceleration being so low, so I pulled out another equation. I pulled out my velocity equation, which, if you remember, was right here. So I thought, why not? I've got time information. I could plug the time into here and find out what the velocity is. I can also now work from the third formula to find out velocity. What often happens in problems is this. They'll ask you information, you know, how far has it traveled, how fast is it traveling at this time. So there's kind of an A, B, C, D parts to the problem. Often what happens is once you get the first part solved, everything else gets easier. Maybe. Not always the case. But a lot of times, once you've used one of these formulas to get that first part solved, then you can go, oh yeah, any of these other formulas now work, now that I'm getting more things understood. So I did use this formula, and the V0 was 0. I plugged in the information I now had, and it told me that by the time I get to the other side of the intersection, I'm going 11 meters per second. So that's like 20-something miles an hour, right? 22, 23, 24. So that's a pretty good speed by the time I'm at the other. I've got to time myself next time I'm crossing a big intersection and see how much time it really does take. 5 seconds seems long, but that's a pretty good speed at the other side. Or, as I was suggesting, we could have used formula number 3, and that would have worked as well. Now, what happens now with these formulas is, now I've got a way to check my answers. Because if I used, you know, method 1 to solve the problem, but there's a second formula that I could have used, I can go back and check. Now, when you're doing homework, that's a really good time to practice using different formulas to go back and double check or triple check some answers. During the midterms, I understand that you want to be able to work more quickly. And so you build up experience by solving this multiple ways, and you go, you know, I can solve faster if I take this approach. And so by the time the midterms come along, when you have those options, you're better prepared to decide which option to go with, okay, on an exam. And so, yeah, the midterms, you know, these are, you want to be able to get through the problems, but, you know, you want to get through them in a timely fashion, too. You want to be able to look at a problem and start setting it up and working towards a solution. Here's another example, braking distance. So this time I've got a car, it's not picking up speed, it's slowing down. And so what we want to do is, here's a car. Now I could see, you can tell that I don't read thoroughly, right? So I need to stop and read this thoroughly until I understand it, and then I need to read it again. It says estimate the minimum stopping distance for a car. And it tells us that the problem is best dealt with in 2 parts with 2 separate time intervals. First of all, there's a time interval between when the driver decides to hit the brakes until the braking begins. So there's a delay between when you've decided you need to brake and when the braking will actually, is a reaction time that's going to take place there. And that's what they call it. So they're saying that for a driver, a reaction time typically for an alert driver is about half of a second. And during that time, the speed will continue to be constant. So for a half second, we want to include constant velocity. And then after that, we're going to have this thing slow down. Okay, so let's see what numbers they've got here. Here we are traveling along. The speed is at 14 meters per second. And for a half second, it takes a half second until we hit the brakes, till the brakes begin to slow the car down. So there's going to be a reaction time, and during that reaction time, we're going to travel a distance that's 14 meters per second for a half second. So that sounds like 7 meters, maybe. And then during the braking, now during the braking, where did they tell us the acceleration? Okay, I read it carefully. I thought I understood it. I guess I have to read it again. Anyway, they tell us here that the acceleration is -6 meters per second squared. That's going to be important, but I don't see it up above. So I think what we're going to end up doing is going with this number. Let's see what happens. Oh, I see. There's more. Aha, the second time interval. So during the second, that's a lot to read. The second time interval is the actual braking period. Now we're going to have an acceleration not equal to 0. We're going to have a slowing down, a deceleration. Stopping distance, initial speed of the car. Aha, here we go. So during that, the acceleration is going to be -6, and that's because we've already designated the velocity. Remember when we talked about the velocity on the previous page? So what happens here is, if I call the velocity positive 14, I've decided that that direction's positive. Okay, so it's implicit. If I'm going to say the car is traveling at a plus 14 meters per second, then when it comes time to write in the acceleration's got to be in the opposite direction. Okay, so I could have done this. I could have said the initial speed was -14. If the initial speed were -14, then in order to slow the car down, I would need a +6. So they need to be in opposite directions. Now I can keep track of that in the mathematics. We'll see a couple different ways to make sure that the signs are making sense. Okay, got it. That was a lot to read. The graphs. So I do want to spend some time on the graphs. So I almost feel like this is so important in setting up the problem. So here we go. I'm labeling v as a function of t, and see how I have time set out. Now initially I don't know how much time this is going to be, so I'm just guessing or estimating how many seconds I might need to bring this car to a stop. I hope it's not too many seconds. But the velocity is starting out at 14, and it's going to be nice and constant at 14 for half a second. And then at the 0.50 second mark, I'm going to begin slowing down. I'm going to begin the acceleration process. Now I'm going to tend to, whether something is picking up speed or slowing it down, I'm going to call both of those acceleration. So sometimes I'll use the word deceleration, but in any case, I could refer to this as a deceleration or an acceleration. Kind of falls in the same category. So there's going to be a deceleration taking place here, and that's what v is going to look like as a function of time. Now x, on the other hand, if I have a constant velocity, that means that x is going to be a straight line with a slope of v, 14 meters per second, for the first half second. So that portion is a straight line. And then when the braking begins, remember when we look back at those formulas for constant acceleration, the x formulas are parabolas. So I'm going to have some kind of a parabola that represents a slowdown. This is x as a function of time, so the slope has to gradually drop off. How do I know when I've completely come to a full stop on an x versus t graph? If it's an x versus t graph, a full stop means that the slope is 0. So once I've done this, then the car is stopped and it just stays at the same value of x until it starts moving again. So yeah, so I've got a straight line for half a second, and then I've got a parabola that brings us to a stop. Okay, so a lot of things to think about here, right, with these problems on motion. Okay, so during the constant acceleration, I'm going to write down a formula for constant acceleration. I'm going to call x not equals 0. The velocity is 14. The time is 0.5 seconds. This drops out of my formula. I can say x is equal to v times t. That's 14 meters per second for half. That's 7 meters. So during the constant velocity period, car's going to travel 7 meters. Now I'm going to start the whole problem over again. I am going to shift my coordinate system. Now, I don't know if that's what they intended us to do, but I think I'm going to do this. So what I'm going to do is, I'm going to say with this part of the problem, I am done. And so I'm going to put that out of my mind. I'm going to redesignate my starting point, x naught, to be x naught equals 0. Now the reason for that is it'll make my formulas easier. And I'm going to, when I'm solving problems, I kind of lean in the direction of resetting the coordinate system rather than using the same coordinate system all the way through. So if it's going to make the problem easier, I'm going to pick up my coordinate system and move it, and that's what I did. So for the second part, x naught is equal to 0. The acceleration now is minus 6 meters per second. They wanted to know information not on time, but on displacement. What's the braking distance, not the braking time? And so I brought out the formula that has v as a function of x. And since I designated x naught to be 0, I can let this just drop out. Now, to me, that makes it a little easier. A different person might say, but couldn't I start with my 7 meters and put that in here? So with my approach, at the end, whatever I get, I'm going to have to add numbers together. So the reaction time resulted in a 7-meter displacement. The constant acceleration of braking, plugging numbers into this formula now, I've got a minus sign here, v naught squared. V naught was 14 meters per second. I've got a minus sign in my acceleration. The minus signs cancel. And it tells me that the distance I'll travel is 16.3 meters during that time. And so 7 meters during the reaction time, 16.3 meters when I actually have the brakes on. The total distance comes from adding those together. If I had taken the 7 meters from here and used it as x naught and kept the entire formula, then that would have been kept. The formula would have been a little more complicated, but it would have been done once I got the answer. And again, my preference is to break it up, add everything together at the end of the problem. Okay. Now I also wanted, I'm always curious on these problems, so I typically end up solving for more than what they ask for. If I'm doing homework or I'm looking at an example, because what's going to happen is, the whole idea is for you to develop skills of, hey, when I get in a new situation, how do I set things up? And so, this is a way to extend the problem, maybe ask some other questions. I was curious, how much time did it take for the slowdown during the braking? And the braking itself took 2.33 seconds, and I got that by taking the v equals v naught formula. Remember, when I stopped, my velocity is 0. So v is 0, it's v naught, that's the minus 14, and then the a here is minus 6. So the minus signs cancel, 2.33 seconds. The total stopping time then would be a half second for this part during the reaction time was a half second, and now we know that this was 2.33 seconds and an additional distance of some number of meters. Okay, so we're kind of, that's it for today. So we'll stop there. We've got one more session, I think, to finish up Chapter 2. We're doing Chapter 2 very thoroughly. Make sure that you're staying caught up. I want to put the extra time into Chapter 2, make sure that we're really looking at everything. Chapter 3 will be easier that way. Chapter 3 is kind of a continuation. So make sure you're staying caught up. Any questions at all, stop by office hours. Let's get any questions answered early on. Sometimes it's really simple. In fact, I'm going to claim most of the time when students come in with questions, they end up going, oh, that's how it works. I get it. Great. So stop by office hours, and we'll see you guys next time.